In this recitation, we would talk about the Boltzmann machine, the relationship between Boltzmann machine and Hopfield network, and also the restricted Boltzmann machine, which is known as RBM. So first of all, there will be a brief introduction of Boltzmann machine and what is actually doing. And so on this graph, and this is what is like Boltzmann machine is look like and is quite similar to a Hopfield network. But the only difference here it is that in each node in the activations, it is not deterministic. Like whether if it is below zero and the node will be turned off, and when it's over zero and the node will be turned on. So here there will be and so for the activation there will be a probability function, and whether it will be on or off, it will be determined by a Bayesian distribution, as we will be saying very soon later. So the Boltzmann machine was first created by the Professor Hinton in 1985, and it is a generative unsupervised models, and it involves learning a probability distribution from an original data set and using it to make the inferences about the data that has been never seen before. And the network itself is a symmetrically connected, the connected the neuron-like unit, as we can see here. And each of the neurons here, it makes the stochastic decisions about the whether to turn on or turn off the node. And for the Boltzmann machine, which is it is quite it is quite cheerful, is that it has a simple learning algorithms, so that it allows them the to discover the complex representations in the training data set and help us to discover the interesting features in the data set. So next, it will come up with the stochastic dynamics of the Boltzmann machine we mentioned before. And here it is the Boltzmann machine formulas we will see. And this one, when a Boltzmann machine for each node I here, it is given the opportunity to update its binary state. So in the Boltzmann machine, each node has two states, both binary states, 0 or 1, similar or same as the Hopfield network. And first of all, it would have this one is called a total input function. And there will be the ZI will be added with a bias term VI, and also added with the sum of the multiplications of the weights Wij with the nodes Sj. So the Wij here is the weight between the nodes, and Sj here it doesn't also it has other meanings. The J means the Sj's is the nodes that has already been turned on, and then it will be fed into a activation function, which here it is a logistic function. So because the logistic function it is distributed, its function range would be ranged between 0 and 1. So we can use it to interpret it as a probability distribution, which is the Bayesian distribution. And the probability here, it means the probability to turn on SI node, the probability for it. And so if the units are updated sequentially in any order that does not depend on the total inputs here, the network will eventually reach a Boltzmann distribution, and it is also known as a equilibrium, which means the vector don't want to move to other states. And so the probability of the state vector V is determined by the energy of the state, and relative to the energies of all possible binary state vectors, which is look like this, the probability. And also similar to the Hopfield network, there will be a energy term. And this is the energy function for the Boltzmann machine, and we want to make it as low as possible. So if the weights on the connections are chosen so that the energies of the state vectors represent the cost of those state vectors, and then the stochastic dynamics of a Boltzmann machine can be viewed as a way of escaping from the not so good local minimum while searching for other low cost, lower minimums. So the total input to unit I here represents the difference in the energy depending on whether that unit is off or on, and the fact that the unit I occasionally turn on, even if the ZI here it is negative, because it is a probability term here. And so there comes up with the reason why we want to make it into a stochastic form, because we want to let the state, which is currently at a local minimum, we want to let it jump from the current energy barriers and to another, the lower state, uh, so that it is possible for this vector state to finally went into a global minimum. And so the search at this term can be improved by the simulated annealing, and the scale, it is scales down all of the weights and energies by a factor t, which is by factor t, and it is known as the temperature in the physical system. And so by reducing t, and usually the t we will start with a high value and finally reach to a small final value. And it is possible to benefit from the high temperatures, which with the fast equilibration, and to have a final equilibrium distribution that makes low cost solutions usually will be optimal. The ideal would be a global minimum, and to then those high cost ones. So finally, when the temperatures got zero and the Boltzmann machine will be, it means when the temperature got zero, it means the probabilities, it will never, no longer have a random state. It will be, all of them will be deterministic. So the Boltzmann machine at this time, it will depreciate into the Hopfield network. So this is kind of a perspective that to relate the Boltzmann machine with the Hopfield network. And from then on, there will be the how to learn the Boltzmann machines. So when we want to learn or train the state vectors here, we would, as usual, deep networks, we will want to optimize the weights of W and B in the network so that to make those state vectors good and to reconstruct the state vectors to the original data. So more specifically, the aim is to find weights and biases that define a Boltzmann distribution, the equilibrium, and where the training vectors have the high probabilities to as the original ones. So what can we do by updating the W? We want to update. We can take a differentiation of this with respect to the W inside here, so that we can get the partial gradient of the uh, weight parameters Wij from the energy term. And then it can be shown that from this term, from the log likelihood, and there will be the gradient of Wij. So overall, the Boltzmann machines, when we want to learn it, and it can be used to, and the Boltzmann machines are used to solve two different computational problems. One, it is usually called the searching problem, where it means that the weights on the connections, Wij, are fixed and are used to represent a cost function here. And the stochastic dynamics of a Boltzmann machine then allow it to sample the binary states and that have low values of the cost function. And the other problem is the learning problem. Here, the Boltzmann machine is shown a set of binary data vectors. It must learn to generate these vectors with high probabilities, like the maximum likelihood as what maximum likelihood estimator is doing. And to do this, it must find the weights on the connections so that relative to other possible binary states, other possible V's, the data vectors have low values of the cost functions. It means also means have low energy value function values. So to solve this learning problem, the Boltzmann machines have to make many small updates to their weights, and each update requires them to solve many different searching problems. So in this term, it means when we want to do the learning algorithms with the Boltzmann machining, it is very slow in the networks. But when we make some restrictions or assumptions on the original network, the speed would be much faster, and that's why it comes with the restricted Boltzmann machine. So I will do the introduction for the restricted Boltzmann machine, RBM. And so RBM itself, the target of using RBM is to make the Boltzmann machine powerful enough to represent complicated distributions. And we consider in this model that some of the variables are never observed and they are called the hidden nodes as H1, H0, and H2. So by having more hidden variables, we can increase the modeling capacity of the Boltzmann machine. So RBM further restrict Boltzmann machines to those without the visible to visible and hidden to hidden connections. And after learning one hidden layer, there's one thing need to mention, and the activity vectors of the hidden units can actually be treated as the data for training another RBM, which means after we train this RBM, we can use the hidden layers as the inputs, as the visible nodes, so that we can repeat to learn as many hidden layers as we want. And after learning multiple hidden layers in this way, the whole network can be viewed as a single multi-layered generated model, and each additional hidden layer improves a lower bound on the probability that the multi-layer model would generate the training data, which means the performance of the whole network would be better than a single RBM model. And I would do interpreted the RBM from the energy-based model perspective. So first of all, and with the restrictions of the RBMs, the hidden units like the H0, H1, H2, they are conditionally independent given a visible layer, and the energy function of the RBM is defined as this, which is the linear combinations between the offsets BC and HV vectors, and the multiplication between HV and with the matrix W, and W here means the weights connecting the hidden and visible units. So this can be translates directly to the following free energy formula. this one is BV, and we used a log to mitigate the effect of the exponential, and this one, becomes a it becomes a free energy form. So the energy-based model function can be interpreted as this. And this one is the free energy function as we seen before, which is this one on the right. And the energy-based probabilistic models define a probability distribution through an energy function. So it will be interpreted as the following, as this one. And z itself is a normalizing constant, which makes the term in this function into a probability function. And because of the specific structure of RBMs, visibles and hidden units are conditionally independent given one another, which is without the connections between visible nodes and the hidden nodes. So using this property, we can write the functions into the independent conditional probability forms. So given V and would this a conditional independent, so we can write it into a multiplications between the conditional probabilities. And then because we usually assume that Vj, the numbers the Vj would only be 0 and 1. So we would obtain from these two functions and the probabilities version of the usual neural activation function, we choose it to the sigmoid. So after then, we can rewrite the free energy functions into this form, which is quite explicit. And then we would move on to the interpretation for RBM from the deep network perspective. So RBMs itself are the shallow two-layer neural nets, and there is no intralayer communication, and this is the restriction of a RBM. And each node is a locus of computation that processes the input and begins by making the stochastic decisions about whether to transmit the input or not, which can be seen in the probability in this one, in these two terms. And each visible node takes a feature from an item in the dataset to be learned. So for example, from a dataset like the MNIST, and the pixels could be 784. So the neural networks that process them must have the 784 input nodes, which is as the similar pixels the images have. And each visible node here would receive one pixel value for each pixel in one image. And follow that single pixel value x through the two-layer neural net. And at the node 1, as we can see here in the plot, x is multiplied by a w and plus a bias, and then go through an activation function. So the output of the activation functions would give us a kind of probability we can be seen before in this version. And in an overview of how the network would be working, so we can see the process in this image. And each x is actually multiplied by a separate weight and then do the things plus a bias, and all of them would be fed into a activation function. So if these two layers were part of a deeper neural network, the outputs of the hidden layer, this one, the hidden layer 1, will be passed as inputs to the hidden layer 2, which was mentioned before. So this one would be the new visible layer, and the 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 nodes inside this layer would be fed into the second hidden layer. And so repeat this process as many as you want. And in this kind of term, the multi-layer RBM would be looks quite similar to an autoencoder, which functions similar to the RBM. But one thing need to know is through when you do the updates of the weights, which is in the backward, this is how the multi-hidden layers RBM will be working. And the whole process looks quite similar to the autoencoder. So first of all, when we do the backward, um, so when we do the backward, we would feed the activations in the reverse way. But there's one thing need to notice is that these biases, when we output the gradients, the biases added to the gradients, it is a totally new bias. So so this kind of thing means that the hidden bias helps the RBM produce the activations on the forward pass, but the visible layers biases here, it helps the RBM learn the reconstructions on the backward pass. So they have so because they have different functions, so they are independent or they are different. So when we do things in the reconstruction process, and here the activations of the hidden layer 1 would become an input in a backward pass, and they are multiplied by the same weights as we used in the forward pass. So the sum of those products, which is quite similar to the forward pass, would be added to a visible layer bias. And the output of those operations is a reconstruction of this pixel. And we can see this kind of thing in a probability perspective. So the RBM, it uses the input when it does the forward pass. It uses the input to make predictions about the node activations. So in a conditional probability form, we can see that given x and the weights w, we can get the probability of the activations. And in the reconstruction form, we are doing things in a reverse way. So when we are given the w and a, we want to estimate the distribution of x. So it's kind of an estimate of what the activation or what the original pixel image it would be. And combine those two things together using the total probability formula, we can get a joint distribution between x and a. A is the activation. So this kind of thing is quite similar to what is known as the generative model. So as a whole, the reconstruction is making the guesses about the probability distribution of the original input. So let's imagine that both the input data and the reconstructions data, they are following a distribution of the normal curves or the normal distribution. It may be look like this. And to measure, and we actually want the two probability distribution getting closer to each other, as closer as much as possible. So we want to measure the distance between the estimated probability distribution and the ground truth, the real distribution of the input. And usually RBM uses what is called, and what we have used, the KL divergence. It's seen as this. And the KL divergence measures the non-overlapping areas under the two curves. And the RBM's optimization, or the target of the updating the weights, is to attempt to minimize those areas so that the shared weights, when multiplied by activations of hidden layer, would produce a close approximation of the original input. And we could see that the weights, when we do the backward pass and when we update the weights would slowly come to reflect the structure of the input, and which looks like quite similar to this. So the whole learning process would look like two probability distributions converge step by step. And so this is all about how RBM can be seen with three perspectives, and talk about the usage of RBM. So once the RBM learns the structure of the input data as it relates to the activations of the first hidden layer, the data can be passed one layer down the network, and your first hidden layer takes the role of the visible layer, as we mentioned before. So the activations now becomes your input, and they can be used to produce another set of activations. And these kind of things, because they look quite similar to the autoencoder, so usually the RBM is used to initialize the weights for the autoencoders.
All right, welcome to Recitation 11. My name is David, and today we'll be going over some of the code for Hopfield networks, stochastic Hopfield networks, Boltzmann machines, restricted Boltzmann machines. This page has all the code where we implement the networks, as well as the corresponding trainers here that can be used to train those networks. This is all in Torch, and it can be run on CUDA for fast training. So at the top here, we have a couple helper functions that we're going to be using throughout this page. First of all, we have rescale and discretize. So rescale, we generally assume that it will take in a vector or a tensor of zeros and ones. And it would rescale zeros to be negative ones and ones to be ones, because we want our Hopfield networks, the values to be a negative one or one. And that's generally called after using discretize, because discretize takes in, let's say, a range of numbers from 0 to 1, not necessarily exactly 0, 1, and then switches it so that it snaps to the closer number 0, 1, and then we call rescale to make it negative 1 and 1s. And then we have a function that generates vectors, or generates random numbers with the same shape as template. which is also used in noisy fields. We'll talk more about noisy fields when we get to stochastic networks. Then we have this update function, which we'll talk about in more detail, but simply put, it aligns each of the values to its corresponding field. So remember in lecture that in every iteration for the networks, we compute a field for each node, and then we flip the node's values to match the field. And this is basically what it does, in place at values. And this is just a good thing to remember, not just for this recitation, but in Torch. Generally, if there's an underscore before a function name, it means that we would want it to be in place. Now we have an abstract class called abstract loopnet. So this is an abstract class that all our other networks inherit from, and it has a bunch of methods that are going to be constantly used throughout the page. It takes in num units as one of the arguments, and that's just simply the number of nodes in the network. And for later Boltzmann machines, we'll have another argument that takes in the number of hidden units as well. We initialize with Xavier normal initialization. And then if fixed weight is true, we fix the weights using this function. So there's a lot of just tensor manipulation here, but what we basically want this to do is force the weights to be symmetrical. So updating node I from J would be the same as updating node J from node I. And how this basically does is takes the weights matrix, transposes it, adds it with the transpose, and takes the average between the two, and then stores that as a new symmetrical weights. Next, we have compute fields. This is not implemented in an abstract class because a lot of the different networks have their own way of computing field. Compute energy uses the later to be defined compute fields and then follows the exact formula in lecture we went over for computing the energy. For update, again, I believe that hot field networks directly use the hot field and stochastic fieldnet directly uses the update function. But as you can see, for stochastic networks, there's an additional element involved. So this is going to depend on what network we're implementing later. Run iters takes in invals and num iterations. This essentially starts with the values at invals and just iterates through the network, updating the values for num iterations. And you can see that it uses the function compute fields to get the fields, then the update function to update the values with the fields in place. Next, we have forward. This just calls run iterations. And a small thing to note that is, since this is inheriting from torch.enn module, if you just call net and then parentheses with the inputs, it will automatically call forward. Now we have another function here called inference. And this is generally used for stochastic networks because stepping one time in a stochastic network, well, since it's stochastic, there are a bunch of different results. And it's not necessarily the best option to just step through it 5 times and just take the final output there, because perhaps it found a good result earlier, but then ended up going to a bad result, or it just randomly moved around in the space. So what this basically does is it again takes in invals, num iters, and then num inference iters. It first runs for num iterations to try to find a good place to start the inference. And then this is just a filler that we're going to return later. Now, after finding a good spot that we want to start the inference, we, for num inference iters, basically do the exact same thing, update the fields and the values, and then add the values at every iteration to val's average, and then average out the values with the number of inference iterations. As mentioned before, this is so that as the network iterates through, especially a stochastic network iterates through a certain space, it can take the average of the places it's been to find the final conclusion. And as we'll see later in the notebook, this actually ends up returning a better result than just calling forward. So now we get into hot field networks, and this inherits from abstract LoopNet. The weights are defined as a torch tensor num units to num units because we update all the units using all the units, and we initialize the weights with Xavier initialization. For compute fields, we just multiply the weights matrix with the passed in values, and for the specifics, we unsqueeze the first dimension because vowels is batched, and then we unsqueeze the last dimension of vowels because we want it to be a matrix multiplication, which we end up just removing the last dimension from anyway. So in some sense, you can kind of think of this as a linear layer, sort of, with the inputs being the number of units and the outputs being the number of units, and the weight transition being the weights matrix in the network. To update, we just call the in-place update operation that we defined up here. And to remind you, this is just updating the values in place to reflect the field that was computed earlier. So that is hot field nets. After hot field nets is stochastic hot field nets. And stochastic hot field nets follow a very similar structure to hot field nets, except it first takes in a temperature as one of the initialization arguments. The compute fields is the same, but in the update function, we take in the fields and then pass it to a function called noisy field along with the temperature. And up above, noisy field is defined. And to go over what role temperature plays here is in a deterministic hot field network where we don't have temperature. If a field is 0.5, the value at the next iteration for that node will deterministically be assigned to 1, since 0.5 is closer to 1 than -1. However, in a stochastic hot field net, there is a chance that 0.5 is still assigned to -1, and how likely it is to be assigned to -1 or instead of 1 is controlled by temperature. So if temperature is 0, then essentially what we have is a deterministic hot field network. 0.5 will always be assigned to 1. However, as the temperature gets higher, there's a higher chance of 0.5 being flipped to -1 than 1. And the way we implement that here is by generating some noise and then weighting that noise by temperature, so that there's a chance that the field will be added or subtracted something and then flipped to the opposite side. And as we mentioned, if temperature is 0, we see that this entire term is canceled and it just returns field. So it acts the same way as a deterministic hot field network. So that's stochastic hot field network. After that, we have Boltzmann machines. So a Boltzmann machine is different from hot field network in that it has a lot of hidden nodes along with the units that you specified. So again, Boltzmann machines are stochastic, so it takes in a temperature, and then it also takes in the number of hidden units you want. The weights you can see here is defined by the total number of units by the total number of units. Because in a regular Boltzmann machine, the visible units, the num units here, are allowed to influence each other, and the num hidden units are allowed to influence each other. So the weights matrix is in the end just a square matrix with the side lengths being the total number of units. And hidden setup, we'll talk more about when we get to the expand data function. The compute fields is identical to hot field networks because there's no restriction on what units can talk to each other. For update, it's very similar, except you see that we have a parameter here called include visible. And this is basically because sometimes we don't want to update visible units, namely in the expand data function, where we just want to update the hidden units at every iteration. And besides that, you see that everything else is the same as the stochastic hot field networks, except that if not include visible, we just put back the original values for the visible units in the result. Now we get to the expand data function. Intuitively, this is used when we want to generate the random, quote unquote, random hidden units from the visible units. So this takes in the visible units and then the number of samples. So batch size is the first dimension in the visible units. And there's a couple of things going on here, but it's basically just making a box to put the hidden values in. To give a high-level idea of what is going on in this for loop, basically we want to generate the hidden values when we're given the invisible values for each sample. So we first start by randomly initializing hidden values and letting the network iterate a few times to see what the hidden values end up being. And then we take those hidden values and return them along with the visible values. So more specifically, we generate random values for the hidden values from 0 to 1. We copy them into the values array. We do some math to write in the values, and then we put them together with the visible values from earlier. Then, for hidden setup iter as many times, we just do the regular compute the fields and update the values, only updating the hidden ones by this parameter include visible right here. And then once we're done with that, we just set the new val as the val we're going to return, as we have given the initially randomly generated hidden values some semantic meaning by the end, dependent on the visible values here. And then lastly, we just concatenate the values in the first dimension since we're batching and then return it. So that's what expand data does. And now we have finished covering Boltzmann machines. Lastly, we have restricted Boltzmann machines, which is in some sense a lot simpler than Boltzmann machines because the visible units can't talk to each other and the hidden units also can't talk to each other. The only connections that are allowed are between the visible units and the hidden units. This is reflected in the weights here, which is from hidden units and the visible units. I like to think of restricted Boltzmann machines as almost like a linear layer from the visible units to the hidden units, and the weights would be the same as here. Note that we do not actually have hidden setup iterations parameter here, and you'll see when we get to the expand data section. For compute fields, we do things a little differently because in Boltzmann machines, we could just run the regular we could just run the same thing we did for Hopfield networks since there was no restriction on what units can talk to each other. But here we have to separate it into two parts. So we first generate the hidden units from the original visible units, and then generate the visible units from the original hidden units, and then concatenate the two results and return that as our fields at the end. So that's the restricted compute fields function. The update function is the same as we've seen for stochastic networks. And finally, in the expand data function is a little different from regular Boltzmann machines. So the key point here is that the visible units stay the same, and we only want to generate values for the hidden units. And since the hidden units only rely on the visible units, which stay constant, we only need to do one iteration of computing fields for the hidden units instead of trying to get it to converge to something as we did for Boltzmann machines. So this code is essentially the same as the above one, except we don't have the for loop. So we make a box for the new hidden units to go into. We put the new hidden units and the visible units together, and then we just compute the fields here as we do above. However, one thing to note is that we reassign the original visible units to the final units that we're going to return, since we don't want the original visible units to be updated from the random stuff that was in hidden values in the beginning. We just want to change the hidden values to match the visible units. So that's the expand data function, and we've covered all the networks. Now let's go through some of the training wrappers for the networks themselves. And the training wrappers are generally going to be almost the same, except for a small difference in the Boltzmann machines. So the Hopfield train wrapper is a torch module, and then as the initialization arguments, it takes the net, which should be instance of the type Hopfield network, and the number of evolved iterations. We'll get to what that is in a second here. The forward, it takes in invals. First, we fix the weights, figure out what the batch size is, and then we run the net num evolve iteration number of times. So remember in lecture, we had patterns that we wanted to learn, which is invals here, and patterns that we didn't want to learn. And recall that in lecture, we generate the patterns we didn't want to learn by starting from the patterns we did want to learn, and then letting the network evolve a few times to see if there's a local minimum next to the patterns we want to learn that we want to pull up. So that's basically what evolve values is, since we're starting it in vals and then running the network for num evolve iterations. Then we generate the positive terms. It's the same formula we saw in lecture where we take the transpose and multiply it with the original vectors and the negative term of the evolved values. Finally, we take the weight negative gradient where we take the positive terms and subtract the negative terms from it. And this is flipped because we want it to be negative. Now, one thing is that this train wrapper isn't technically a true loss function so far. Torch, or the trainer, I believe, inferno that we use, wants this class to return a single loss, and then the autograd will look at the loss, do backpropagation to it, and then generate the gradients, yada yada yada. We would want this to be the gradients, and so we have this Lex line, which is essentially a hack where we multiply the weights matrix with the weights gradient, element-wise multiplication, and then normalize it with the number of units. So when you take the derivative of this with respect to the weights, you end up getting back the precisely the gradient that we want autograd to find, just normalized with the number of units. So that's just a little hack to get around the autograder, but you can ignore that and just think of this as the true gradients that autograd is updating with. Now we have a little condition here where if the weights evolve too far away from the initial positions, we just ignore them. And that's because we want to raise up the local minima near the initial weights instead of somewhere far away. So we just have this little condition here that stabilizes training. So that's how you train Hopfield networks, and you'll see that the other trainer wrappers are very similar. Now we have stochastic Hopfield training. And this is a little different. So for this and Boltzmann machines, the main difference is that when we do the evolve vals, so the values that we want our network to not learn, instead of just starting at the input vals, the patterns that we want the network to learn, we instead randomly sample. So that's basically what this is doing. We randomly sample num-rand sample number of negative samples, and then run those negative samples for this many iterations specified in the init. And those are the sample vals that we don't want our network to learn. So to repeat, the parallel for this in Hopfield, in a regular Hopfield network would be evolve vals. And the difference is that instead of starting from the patterns we want to learn, we just start from random patterns. The rest is, I believe, exactly the same. The positive terms are computed from the patterns that we want the network to learn, and we subtract the patterns we don't want the network to learn from them. Next, we have the Boltzmann machine. This is basically exactly the same. The only difference is that when we generate the random samples that we start from to learn the negative patterns, we still need to expand them. So we randomly generate the visible data, expand data to learn the hidden values in terms of the visible units, and then do the exact same thing here. For restricted Boltzmann machines, it's customary to go back to what we did for Hall-field networks and define the negative patterns starting from the positive patterns. So this code is exactly the same as Hall-field networks, except we expand data for the visible units that we get passed in. That's about it for this section of the code. Then we'll go to the notebook next, where we see a couple examples where we use this. Now we're at the section where we go through a Jupyter notebook and see some examples of the code that we just went through. I'm running this on Colab. We'll release the zip file with the recitation and the notebook later on. We import some stuff that we need. Oh, we didn't go through the RBM demo utils, but what that basically does is it just has a bunch of functions that is useful. Here, it has a little class that loads in the MNIST dataset the way we want it. And the important thing here, well, the only change from this, between this and the regular MNIST dataset, is that it takes in the image, which is a 28 by 28 image, which ends up being 784 length vector. And then we append a one-hot vector representing what class it is at the end of the 784 vector. So in the end, we have a 794 vector. The first 784 points being just the image flattened, and then the last 10 being a one-hot representing what class it is. So an example image is 5, and this just prints out what class it is. First, Hall-field networks. So we train a Hall-field network with 794 units. We initialize a trainer. The 1 here, if you can refer back to the code earlier, means just to evolve once for every iteration to generate the negative samples. And then we train. With the trainer, we defined above the MNIST dataset using identity loss. For 300 iterations, a batch size of 500, the Atom optimizer with 0.01 learning rate, and just the name of the folder that we want to save the checkpoint. Here we load in a random example from the MNIST dataset. We basically, quote unquote, zero out the last 10 places of the vectors. And note that this ends up being a 1 by 794, so we index into the first dimension, and then set -1 as the last 10 places in the 794 vector. And that's because we would like the Hall-field network to not only tell us the nearest convergence of the image, but also try to fill in the missing blanks in the last one hot vector. We send it to CUDA, and then we run it for 1,000 iterations. So this is the example data. And this is actually wrong because the one-hot vector representation is computed after it's zeroed out already. So this is just a random thing. And then this is the result of running our network 1,000 iterations. So this is the nearest local minimum when we pass in this image up here. And the interesting thing is that we see that it had indeed correctly filled in the one-hot vector at the end and classified this image as 8. Next, we look at stochastic Hall-field networks. It's essentially the same as the Hall-field network, except we have a little temperature here. This is the number of random samples we generate every batch. And I just set that to 500 because we have 500 positive samples, so we might as well have 500 negative samples. And we run every negative sample for 3 iterations. This is essentially the same. And you can see that the loss decreases pretty quickly and ends up converging to around 0.1-ish. And then we run an example through the network as we did before for 1,000 iterations. And yeah, it does seem like it learned a more representative local minimum for 1 at least, and then again, it classified it correctly here. For more details, you can look through your notebook on your own as we'll release it and reference some of the code in the utils file. Lastly, we have restricted Boltzmann machines. So we initialized the restricted Boltzmann machine with 794 visible units and 500 hidden units with a temperature of 0.2. And then we initialize the trainer with net and 2. And 2 means to evolve twice at every iteration. And we just train it. The loss bottoms out really quickly for restricted Boltzmann. You can see that it only really learned for like 30 iterations, epochs, and then automatically, well, really quickly went to 0. So we again run an example here. Note that we've taken the example 0 at the 1-hot vector at the end, and then generate the expanded version of the example to pass into our network. This is the example. And then this is just running the expanded vector through the network 100 times. And we print out what the network thought, the class the network thought it was, and then the representative image. And you can see that it's really noisy. And that's because this is a stochastic network with the temperature 0.2. So it's possible that it did end up filling in all the blanks at some point, but then just not this iteration. And if you remember, we have a function that kind of takes care of this, which is called inference. So here, instead of forward, we use inference here. We first run it for 50 iterations and then average the next 100 iterations together. And we get a much cleaner image here. Next, we test how well RBM would be if we put some noise in. So basically what this does is read in another example, 0 out the classification, 1-hot vector at the end, put a bunch of noise in dropout, rescale it since dropout automatically scales it with respect to the probability, and then run it through the network. So this is the original image. It's just a 2. This is the image after adding noise. And you can see that the tensor value actually changed here because dropout ended up adding, ended up changing the classification 1-hot vector as well. But this doesn't matter yet since we haven't run it through the network. And this is the result after running it through the network with the inference function. So you can see that, well, the 2 seems to have gotten a lot larger, but it cleared out most of the dots in the background and correctly classified the image as 2. That's about it for the Jupyter Notebook anyway, so thanks for coming to the recitation.